So go ahead, Roy.
Okay, hello everyone. I'm Roy. I will talk, as Lior said, about the expected number of roots of random polynomials over the p-adic. So the problem that we have that if we have a polynomial with coefficients IID random variables in some ring R, and we take and we denote CF to be the number of roots the polynomial has, we ask the question, what is the expected number of this polynomial over the ring of p-adic integers? These questions in other rings have been researched before. One result of Ibragimov and Maslova is that the expected number of roots of the polynomial in the reals is about log asymptotically log n for every distribution with expected value of 0 and variance 1. Over the rationals, using results of Bary-Soroker, Kokolopoulos, and Kozma, which is also based on Konyagin, it is possible to prove that in the rationals, the number of rationals root, the expected number of rational roots is tending to the probability that the free coefficient is 0 for any distribution with a finite moment. On the other hand, in the p-adic integer, most result about random polynomials is when the coefficients are distributed according to the Haar measure on the p-adic integers. One result of Boller, Goldstein, Maus, and Rosenberg is that the polynomial is irreducible in probability tending to 0. From result of Evans and Igoza zeta function, it is possible to prove that such polynomial has average of p divided by p plus 1 expected roots in the p-adics integers. My main result is that if the distribution...
Can you go back to the previous slide?
Yeah, sure. Yeah, I actually didn't open the chat for the questions.
So it's not only that it goes to 0, it goes super exponentially fast? Or?
Yeah. Yeah, but this is only for the irreducible. It's not telling about the number of roots.
Okay. Thank you.
Yeah. So my main result is that if the distribution of the coefficients modulo p is not a constant, then the expected value of the number of roots is the expected number of the number of roots of the polynomial f0 and another constant, as you can see here, and some error term. The polynomial f0 is f of p x. From this result, we can compute a few other specific distribution, such as if the coefficients are plus or minus 1, both with equal probability, then the expected number of roots is tending to p minus 1 divided by p plus 1. If the coefficients are 0 or 1, both with equal probability, then we have an expression for the number of roots with an error term, and also we have an expression if the coefficients are distributed from 1 to p minus 1 uniformly. Some heuristics using computers, we have that we can see that polynomial with plus or minus 1 coefficients, we can see the difference using computer to compute to compute the results. The dotted line is the expected is the limit, as I found out in my results. Also for 0 or 1 coefficients, we have.
Roy, what are the each axis? What is it? I mean,
each axis is the average of.
What are this number? Is it?
Yeah, sorry.
I mean, you when you give a graph, you always have to say what are, because I'm married to a physicist, and this I learned from her.
Yeah,
you're not allowed to give graphs without units.
So the x-axis, the horizontal axis is the degree of the polynomial, and the vertical axis is the average number of roots. Each dot here is 1,000 polynomials chosen randomly with a computer, and you see here the average of the number of roots, and the dotted line is what my result is saying that the limit should be.
A question?
Yeah.
So the vertical is the average of the number of roots. So there is no more than one root on average. Is there an explanation for that?
Reducibility.
On average, no, there is no the explanation. Result.
It looks magical. It looks like it's a ratio of something, and it has to be less than 1. I don't know.
No, it's not have to be. It's not have to be less than 1.
Okay.
But it's not likely, or it's at least
okay.
Not likely.
But there is an explanation for why it's less than 1, because if you compare it to the Haar measure, no? Because 0 cannot be a root. No? It's
yeah,
not
but even the Haar measure is less than 1.
Yeah, this is but for plus minus 1, it should be less than p minus 1 over p, no?
Yeah,
because 0 cannot be a root, and all the rest are.
Yeah, the thing is
maybe naively at least.
The thing, as Lior said, in the case of the Haar measure, we don't have here the plus the minus 1. So basically, in the Haar measure, we have more roots because of the term of the F0 polynomial, which we don't have here. In the plus minus 1, this is coming from the fact that when the coefficients are plus minus 1, there are no roots which are 0 modulo p. So basically, this is the case in the plus minus 1. In 0 or 1, there are more roots. And there are more roots than 1, as in average, at least for big P. So how do I prove my theorem? So I started with denoting the polynomial fr, which is f of r plus px. Now using Taylor expansion, okay, I can write this fr as following, and I will look on the part of the coefficient without the p, also as known as a Hasse derivative. And if I take a k approximately log n and r that is different from 0, and I look on this vector of the Hasse derivative to k modulo p in the power of k, then it's distributed uniformly in the set of in the space of integer modulo p in the power of k with dimension k up to an exponential arrow. What that gives me, I will prove that later how I got there. What this gives me is that I now know the distribution of the polynomial of fr when r is different from 0, and they are distributed uniformly in this set. Okay. The distribution of fr modulo p in the power of k. Now, what's interesting about polynomials that are distributed uniformly in that set, that their modulo p in the power of k is distributed uniformly in that set, is that I can calculate the number of p-adic roots they have if I know that they're distributed uniformly in the upsilon set. This I will prove later too. And the way I continue from here is that every root that fr has is corresponded to a root of f, which is equal to r modulo p. So this gives me that the number of all the roots of f is equal to the sum of all numbers of roots of fr. Continuing using that on the expected value, so I have the expected value of the f0, which I don't know to compute in the general case, and the other FRs I can compute by using this result. Any question?
Just when you say that it distributes uniformly on the upsilon k up to an exponential term, is it exponential in k, n, p?
Exponential in n.
In the degree. Oh.
Yeah.
And k is logarithmic in n, right?
Yeah. So the first part of the proof that I mentioned before, proving that this vector is actually really distributed uniformly in V up to an exponential error. So I use random walks to prove that. I'm creating a vector with the binomial values, and I defined a random walk inside V, which is nth step is the coefficient Ci multiplied by r in the power of I multiplied by the vector Vi's, and simple computation give us that this is actually the vector that we are trying to show that it's uniformly modulo in the power of pk, modulo in p of power k. And what we can show in this random walk, that if I have nu as the probability measure of the random walk, the Fourier transform on V is bounded by exponent of minus c n in some in any epsilon actually, where for all vector that is non-zero. Using the inverse Fourier transform, it gives me that actually this is the inverse Fourier transform. So because it's a probability measure for the zero vector, the Fourier transform is 1, and I have the main term, which show it's uniformly, and the other vectors I can bound by this bound I found before, and this gives me that this vector modulo p in the power of k is uniform, is distributed uniformly in V. Any question?
Just to make sure I understand, you kind of just, you open the F to write them in terms of like the coefficients, and then you use like a probability theory, like Fourier analysis and stuff like this to bound this.
Yes.
Right. What's that?
For the other part of the proof of computing the expected number of those FR, knowing that they are distributed in the uniformly in the set of epsilon, for this part I created a new definition which I called K-Enzelian root. X in the integer of in the integer modulo in the power of pk is K-Enzelian root of g if the derivative of g is not 0 in x modulo p in the power of k, and I can lift x to the integer in the modulo in the p in the power of 2k to a root of g. These definitions come from the from one of the version of Hensel lemma, which basically say that if k is K-Enzelian root, then if x is K-Enzelian root, then x can be lifted uniquely to a root of g in the p-adic integers. Okay, so this is rephrasing. This is my rephrasing of Hensel lemma. The other fact that is easily can be proved, that if x is a simple root of g modulo p in the power of k, and x can be lifted to a root of g in the p-adic integer, then x is a K-Enzelian root. Okay, this is because I can take the lift of the p-adic p-adic integer and reduce it to modulo p in the power of 2k. And so I find out that x is a Henzelian root, and this is actually give me that any root of the polynomial in the p-adic is actually a k Henzelian root in the case that I have only simple roots modulo p in the power of k. In the case I have multiple roots, in the case I have non-simple roots modulo pk, I can bound this by I can bound the number of roots and get something that will get into the error term. It will be part of the error term. The first bound I will use is that if g is different from 0 modulo p in the power of k, then the number of roots in the p-adic integer is less than the degree of g modulo p in the power of k. And then what I say is that the number of roots of g is less than the expected number of roots of k. Of half k Henzelian roots of g plus the degree of g modulo p in the power of k, half k, multiplied by the number of the probability that g has non-simple root modulo p in the power of half k. And for the case that g is equal to 0 modulo in the power of half k, then I bound it with the degree of g. Computing all of those terms, I get what I wanted to prove, that the expected number of the expected number of roots of g is 1 divided by p plus 1 plus an error term. Any question?
So in this case, you get slightly less than 1 over p, which is, I mean, if all polynomials were Henzelian, then it would be 1 over p, but this is the correction because you have things that are not Henzelian.
Yeah, the number of Henzelian root is always less than the number of roots in the p-adic. So the error term actually is always positive.
I have a question about the first statement in the slide. This is always true, or in probability, or in average?
This is always true.
For g with integer coefficients, p-adic integer coefficients?
With p-adic actually, with any coefficient, it's more also integers. It's based on the fact that I take the linear factors that the roots create, and they give the degree also in modulo p in the power of k. Well, it was a bit short.
Okay, thank you, Roy.
Questions?
Let's thank Roy. So let me just stop the recording.